If you can't count every fish in the ocean, how do governments set fishing limits that entire industries depend on? The global fishing economy moves over $401 billion a year and touches the lives of more than 600 million people. But the numbers shaping it all are built from a mix of scientific method, statistical guesswork, and informed assumptions. Beneath these estimates lies a high-stakes puzzle where getting it wrong can mean empty oceans, lost jobs, and unexpected collapse. So what does it really take to count the uncountable? Every year, the world's fishing industry moves more than $401 billion, enough to rival the GDP of entire countries. That's not just a figure on a balance sheet. Behind that number are more than 600 million people whose livelihoods depend on catching, processing, transporting, and selling fish. In some coastal villages, nearly every family traces their income back to the water. In sprawling cities, seafood markets fuel local economies and feed millions. But here's the twist. All these jobs, all this money, rest on numbers that are, at their core, educated estimates. The Food and Agriculture Organization reports a first sale value of $406 billion for global fisheries and aquaculture. About 61.8 million people work directly in these sectors, on boats, in hatcheries, at processing plants. When you add in everyone who builds nets, repairs engines, or packs boxes, the total swells to well over 600 million. That's nearly 1 in every 12 people on Earth whose work links back to fish. Yet, the data guiding this vast system doesn't come from counting every fish. Instead, it comes from a patchwork of scientific surveys, statistical models, and best guesses. The numbers that set, catch limits, and shape economies are built on methods as much art as science. If you're curious about the hidden science behind these global decisions and want to see how researchers try to solve one of nature's great mysteries, don't forget to like and subscribe. The stakes for our oceans and for millions of people depend on getting these numbers as close to right as possible. Every official catch limit, every quota, every policy about who can fish and how much, they all trace back to a chain of data, models, and decisions. It starts with raw numbers. Fish caught in nets, sonar echoes bouncing off schools, logbooks filled out by captains, and the weight of a day's haul. Scientists feed these pieces into stock assessment models, which try to estimate 2 key points. How many fish are left, biomass at maximum sustainable yield, BMSY, and how much fishing pressure the stock can handle, fishing mortality at maximum sustainable yield, or FMSY. But these models don't just spit out a single answer. They generate a range, a confidence interval, because every step adds uncertainty. Trawl surveys might miss fish that avoid nets. Acoustic readings can be thrown off by mixed species or noisy water. Even the best models rely on assumptions about how fish grow, reproduce, and move, and those assumptions can be wrong. Once the science is done, advisory bodies like ICES or the U.S. National Marine Fisheries Service translate those estimates into recommendations for total allowable catch, or TAC. Their advice includes buffers for uncertainty, often suggesting quotas below the upper limit to avoid overfishing. But then, the process moves into the political arena. Ministers and councils weigh the scientific advice against economic pressures, jobs, exports, and local traditions. Sometimes, quotas are set higher than recommended, with the hope that the models are conservative or that the next year will bring better news. Every adjustment, every leap of faith, adds another layer of risk. The result is a decision chain where uncertainty travels all the way from the first net in the water to the final quota on a government ledger. If the initial data are off by 20%, the final policy might be off by even more. For a $401 billion industry and hundreds of millions of livelihoods, these margins of error are not just academic. They ripple through economies, ecosystems, and communities. That's why scientists are always searching for better methods, and why the stakes for getting the numbers right are so high. Imagine trying to measure something you can't see, hidden in a world that resists easy answers. That's the challenge at the heart of fisheries science. Most fish live out their entire lives far below the surface, out of sight and beyond the reach of even the most determined researcher. Unlike counting trees in a forest or animals on the savanna, there's no way to line up fish and tally them one by one. Instead, scientists have learned to read the ocean through its traces, signs and signals that hint at the life beneath. A net filled with herring, an echo from a sonar ping, a handful of tagged salmon returning upstream, or a few strands of DNA drifting in the current. Each offers a clue, but never the whole story. These are what scientists call proxies, indirect indicators that stand in for the real thing. A spike in catch-per-unit effort might suggest a healthy population, but it could also mean fishers have just gotten better at finding the last remaining schools. A sudden drop in acoustic returns might reflect a change in fish behavior, not an actual decline. Even the most advanced models are built on layers of inference, translating scattered data points into sweeping estimates of abundance and risk. Every method, no matter how sophisticated, comes with blind spots. Assumptions about where fish are, how they move, and how they respond to our tools. This is the paradox of fish counting. The better our proxies, the closer we get to the truth, but certainty always remains just out of reach. The next chapters will explore the ingenious and sometimes imperfect ways scientists try to see the unseen, and why these indirect measures matter so much for the future of our oceans. Dragging a net through the sea might seem like a simple way to count fish, but the science behind trawl surveys is anything but straightforward. These surveys have their roots in the early 1800s, when wooden sailing vessels first towed heavy nets across the North Atlantic, searching for cod and haddock. Today, the method is more refined. Research vessels deploy standardized gear, often with a coden mesh as fine as 1 centimeter, and follow strict protocols for tow duration and speed. The ocean is divided into random strata, with each zone sampled to build a statistical picture of what lies beneath. A single trawl haul can bring up dozens of species, from tiny juvenile whiting to hulking adult cod. Scientists record the weight, length, and age of every fish, then use these samples to estimate the density of fish across much larger areas. But even with all this care, trawl surveys can only offer a partial view. Some fish avoid the net entirely, slipping away before the doors close. Others escape through the mesh, especially the smallest juveniles. The shape of the seabed, the time of year, and even the weather can influence what ends up in the catch. The numbers that come out of a trawl survey are never exact. Recent assessments in places like the North Sea report coefficients of variation, essentially the margin of error between 15 and 30%. That means if the survey estimates 1 million tons of cod, the real number could easily be off by hundreds of thousands. And because trawl gear is selective, favoring certain sizes and species, the picture is always a bit skewed. Still, these surveys remain the backbone of fish population science, providing the longest-running, most consistent data series available. They show us trends and warning signs, but they also remind us just how much of the ocean remains hidden from view. Sonar changed the game for fish counting in the 1970s. Instead of relying on what nets could catch, scientists started using hydroacoustic surveys, sending out sound waves and listening for echoes that bounce back from fish suspended in the water column. This method is especially useful for pelagic species, like herring or anchovy, that travel in huge, shifting schools too fast or deep for trawl nets to track. The process starts with a research vessel moving along straight transects, pulsing sound at a standard frequency, most often 38 kilohertz, into the water. When these pulses hit something denser than water, like a fish's swim bladder, a portion of the sound reflects back. The returned signal is measured as volume backscattering strength, and scientists use species-specific models to convert these echoes into biomass estimates. The math behind it is called echo integration, and it adds up the total acoustic energy from a school to estimate how many fish are there and how big they might be. The echo is a clue, not a certainty. But the method is far from perfect. The strength of the echo depends on both the size and the species of fish, so mixed schools or unknown species can throw off the calculations. Surface bubbles, background noise, and even the tightness of a school can all distort the signal. Calibration is critical. Before each survey, the equipment is tested using known targets to adjust for any drift. Despite these efforts, error margins remain stubbornly high. In the North Atlantic, hydroacoustic surveys for pelagic stocks typically come with a 20 to 40% margin of error, sometimes even more in waters with many species or lots of background noise. Frequency selection matters too. Lower frequencies like 38 kilohertz penetrate deeper and are better for larger, deeper fish, while higher frequencies can pick up smaller or near-surface species but lose range. Scientists must choose carefully, knowing each frequency comes with trade-offs. Even with these challenges, hydroacoustics allow researchers to cover vast areas quickly and non-destructively, something impossible with nets alone. Still, every echo is a clue, not a certainty. The numbers these surveys produce are shaped by layers of assumptions, models, and technical limitations. They are essential for managing pelagic fisheries, but they are always, at best, an informed estimate. One more piece in the puzzle of counting the unseeable beneath the waves. Counting fish isn't always a matter of nets or sonar. For species that slip through traditional surveys, scientists rely on a set of specialized tools, each with its own trade-offs. Mark recapture is one of the oldest. The idea is straightforward. Catch and tag a group of fish, release them, then later catch another sample and count how many are tagged. The Lincoln-Peterson equation, N equals M times C divided by R, turns those numbers into a population estimate, where M is the number marked, C is the second catch, and R is the number recaptured. But the method assumes the population is closed, tags stay on, and every fish has the same chance of being caught. In practice, fish migrate, some tags are lost, and wary individuals learn to avoid capture. Despite these limits, Mark Recapture has mapped salmon migrations, identified halibut spawning grounds, and informed quotas for species beyond the reach of nets or sonar. On reefs and rocky coasts, divers step in. Underwater Visual Census, or UVC, sends trained observers along fixed paths, counting and sizing fish within set boundaries. No gear, no bycatch, just eyes and slates. Detection rates for visible species run between 60 and 90%, but cryptic or nocturnal fish often go unseen. Most surveys stop at 30 meters, leaving deeper habitats unexplored. Even among experienced divers, estimates can differ by up to 25%. Still, UVC remains the standard for tracking reef health, especially when paired with video or stereo cameras for later review. Environmental DNA, or eDNA, is the newest tool. Fish shed genetic traces into the water. By filtering just a few liters and using quantitative PCR, scientists can detect species at concentrations as low as 1/100th of a DNA copy per liter. DNA degrades quickly in sunlight and warm water, and currents can scatter traces, making results less certain. Still, eDNA has revealed rare species and flagged invasive arrivals, filling gaps left by older methods. In the summer of 1992, the docks of Newfoundland fell silent. The cod that had once filled nets and fed families for generations were suddenly and almost completely gone. The Canadian government declared a moratorium on cod fishing, shutting down an industry that had shaped the region's identity for centuries. Overnight, about 35,000 people lost their jobs, fishers, plant workers, truck drivers, and countless others whose work depended on the pulse of the cod fishery. For some towns, it was as if the heart had stopped beating. The warning signs had been there for years. Scientists tracking the cod population saw catch per unit effort, or CPUE, stay high even as total catches fell. This gave the illusion of abundance, a statistical mirage known as hyperstability. Fishers, with better gear and local knowledge, kept finding the last dense pockets of cod, masking the true scale of decline. Official trawl surveys reported a steep drop in spawning stock biomass, falling to just 20% of what's considered the minimum for a healthy, sustainable population. But the models behind the quotas relied too heavily on CPUE and missed cod that had shifted to deeper, unsampled waters. By the time the models caught up to reality, the collapse was already in motion. The consequences rippled far beyond the water. The annual value of the cod fishery in Newfoundland had once topped $450 million. After the moratorium, it fell below $50 million. Unemployment in some coastal towns surged above 30%. Families who had fished these waters for generations faced a stark choice: adapt, leave, or hope for a recovery that still hasn't come. To this day, the cod population remains a fraction of its former size. The cod collapse stands as a stark reminder of what can happen when counting methods fail, models are misapplied, or warning signs are ignored. The loss wasn't just ecological, it was social, economic, and deeply personal for thousands of people. It's a story that haunts fisheries science, and a lesson that getting the numbers wrong can change the course of entire communities. Innovation in fish counting doesn't stop at nets or sonar. Around the world, scientists and volunteers are racing to close the gaps left by traditional surveys, using technology that would have seemed like science fiction a generation ago. Satellite-based vessel tracking is one of the most ambitious efforts. Global Fishing Watch, for example, uses automatic identification system data to map the movement of thousands of fishing boats in near real time. These digital effort maps reveal not just where fleets go, but where fishing pressure is highest and where data might be missing entirely. For the first time, managers can see patterns of activity in remote regions and even spot illegal, unreported, or unregulated fishing that slips past official records. Underwater, the next leap forward comes from machine learning. Baited remote, underwater video systems, BRUVIs for short, deploy cameras to the seafloor, luring fish into view with bait, and then letting artificial intelligence do the counting. Deep learning algorithms have reached 85% accuracy in classifying species from hours of footage, a task that would take human experts days or weeks. These systems excel in habitats where nets and divers struggle, capturing cryptic, nocturnal, or wary fish that rarely show up in traditional surveys. Still, the technology isn't flawless. Rare species can be misidentified, and murky water or low light can trip up even the best trained models. Citizen science is also transforming the field. The Reef Life Survey Project has mobilized volunteer divers to conduct more than 70,000 transects across over 70 countries, building a global database of reef fish abundance and diversity. Trained volunteers follow strict protocols, collecting data that now contributes to scientific assessments and even shapes management decisions in places like Australia and the Mediterranean. Yet, coverage is uneven. Most surveys happen near accessible reefs, and identification skills can vary. Rigorous checks, expert reviews, and photo verification help maintain quality, but the challenge of scaling up remains. Each of these tools fills a different blind spot. Satellite tracking exposes hidden effort. AI video analysis brings clarity to complex underwater scenes, and citizen science expands reach far beyond the limits of research budgets. None of them offers a perfect count, but together they push the science closer to the truth. The hope is that by layering these new streams of data on top of traditional methods, tomorrow's stock assessments will be more robust, more transparent, and less likely to miss the warning signs that once went unnoticed. Every quota, every policy rests on numbers built from fragments and inference. Right now, the future of a $401 billion industry and 600 million livelihoods depends on our ability to trust what we cannot fully see. Uncertainty is woven into the science, but so is hope. Because managing what we can't count perfectly is the only way to keep our oceans alive. If you value the hidden science, join the conversation below.